Hello and welcome to this revision session on quantum physics, which is part of the AQA A-level physics specification. So in today's revision session we're going to focus on the key concepts of quantum physics and see how they work. Now the first topic we want to look at is the photoelectric effect. Now the photoelectric effect is the emission of electrons from a metal surface when electromagnetic radiation is shined upon it. The electrons are emitted off the surface as they're given enough energy by the electromagnetic radiation to overcome their attraction to the nucleus and become free. So the electromagnetic radiation has given those electrons in the metal energy that's ionized the electrons, and they left the surface of the metal and they form something which is called photoelectricity. Now it's important to note that the minimum amount of energy needed to overcome the electron attraction to the nucleus, which is holding the electrons in the structure, is called the work function. Now as electrons require different amounts of energy to overcome their attraction to the nucleus as they exist in different orbitals or different parts of the metal, we define the work function as the minimum energy needed to release an electron from the surface. And the work function is unique to every element since they all possess different electrostatic attractions between their nuclei and the electrons. Now it's important to note that the photoelectric effect is proof that electromagnetic radiation must act like a particle. This is because observations from the photoelectric effect do not follow the theorized behavior of wave theory, because according to wave theory, if the electromagnetic radiation was in the form of a wave as it hit the metal surface, then the intensity of the wave would affect how many electrons are emitted. And in addition, this was not observed in our photoelectric effect, as intensity did not affect how many electrons were emitted in the photoelectric effect. So therefore we concluded electromagnetic radiation could not be a wave in this particular situation. Now according to wave theory as well, because the energy is being slowly absorbed by the metal surface, there will be a delay between the absorption of the energy from the wave and the emission of the electrons from the metal surface. Now this is not observed in the photoelectric effect. Electrons are emitted instantaneously after radiation is shined on a metal. This was proof that the electromagnetic radiation was not a wave, rather it was acting like a particle, and we consider these streams of particles to be called photons, each with an energy of hf. Now it's important to note that an electron in the metal can only absorb one photon at a time. This means the emission of electrons happens instantly, as only one photon is needed to be absorbed by the electron. So it also means the only factor which affects how much energy an electron can receive is the photon energy. Now because each electron can only absorb one photon at a time, the photon energy is the only factor that affects if an electron is emitted. Now the only factor in the photon energy is the frequency of the radiation. Now intensity is not a factor to determine if individual photons have enough energy to make the electrons overcome their attraction to the nucleus. It's important to note it's the frequency of the radiation which determines if there is electrons emitted. The higher the frequency, the more energy each photon has, the more energy received by an electron, therefore it's more likely the energy delivered will be above the work function. So that is the factor that determines if electrons are emitted. So the only factor which affects photon emission is the frequency of the photon, and the minimum frequency to overcome the work function is called the threshold frequency. Now it's important to note that any energy above the work function delivered by the photon goes to the kinetic energy of the emitted photoelectron. So this means the frequency of a photon determines if electrons are emitted and the speed of those electrons when they are emitted. The higher the frequency of the photon, the greater the speed of the emitted photoelectron. We can see this in this particular animation. Here the photons have energy above the work function due to having a frequency above the threshold. This causes photoelectricity. Whilst in this particular situation, photons have energy below the work function due to having a frequency below the threshold, and this causes no photoelectricity. So we can consider each electron in a potential well due to their attraction to the nucleus. The potential well is caused by the electrostatic attraction between the nucleus and the electron. electron. The attraction is dependent on the energy orbital the electron is in. It would be a maximum if it was closest to the nucleus in its ground state. It would be the minimum if it was the furthest orbital away from the nucleus. Now remember, we define our energy needed to overcome the attraction as the work function, which is a minimum energy. Now it's important to note that we tend to give this value in electron volts because the value in joules is so small, and like we mentioned before, the work function for each element is in fact unique. Now like we said, an electron can absorb the energy of one photon at a time to escape its potential well. Now it's indicated that's a key principle of quantum mechanics, of quantum physics. Now this shows us that electromagnetic radiation comes in chunks of energy, the energy of a photon. So electromagnetic radiation is not continuous, rather it is discrete. This means, like we said before, photon intensity is not a factor when the photon does not have enough energy to overcome the work function. So if the work function is greater than the photon energy, hf, there's no electron emission. If the work function equals hf, well, the electron is emitted from the surface of the metal, but it can't move any further. Now again, the electron has passed the threshold of photoemission, so the frequency which brings enough energy for the photon to have the work function is called the threshold frequency. Now below the threshold frequency, intensity does not affect photoemission. Now above the threshold frequency, the intensity can affect photoemission as each photon has the energy to overcome the work function. Now if the work function is smaller than the energy of the photon, the electron will escape the surface of the metal, and the kinetic energy of the electron will be the energy from the photon once the work function is being subtracted. So we can assume in this situation that no energy is lost to the internal energy of the surroundings from the photon. So our equation for photoelectricity is the photon energy equals work function plus the kinetic energy of the emitted electron. So say for example our photon energy was 30 eV and our work function was 20 eV, then the kinetic energy must be 10 eV. So the energy of the photon splits between the energy of the work function and the kinetic energy of the emitted photoelectron, which you can see in these different situations. Now change in intensity will not overcome the work function, so therefore it's only the frequency that affects your photoemission. The intensity can only become a factor once the photon has more energy than the work function, the frequency is above the threshold, since that work function has already been overcome. Now again, the other proof of the idea of why the photoelectric effect is proof of the particulate nature of light is that A, the intensity is not a factor on photoemission, and secondly, there's no delay between the radiation being shined on the surface and the emission of the electrons. So in this example, the photon energy is less than the minimum required for the electrons to escape, so no electrons are emitted from the surface. The photons have a lower frequency than the threshold. In this situation, the photon energy is greater than the work function, so photoelectrons are produced at a range of kinetic energies up to a maximum value. So the photons have a higher frequency than the threshold. Now we gain a range of kinetic energies as the work function assumes all of the emitted electrons are at the surface of the metal, which is not the case in reality. Now the photon energy is large enough in this instance to cause emission, and if that's the threshold frequency, photoelectrons with zero kinetic energy must be produced. So what do we know about the photoelectric effect? It's the emission of electrons from the surface of a metal due to the absorption of radiation. We know that light must behave as particles called photons in the photoelectric effect, as only the frequency of radiation affects whether electrons are emitted, and there's no delay on the emission of electrons after the radiation is shined on the surface. The frequency affects if electrons are emitted and the speed at which they are emitted. The intensity affects the amount of electrons emitted per second, and the work function is the minimum energy needed for an electron to be emitted due to the attraction between the electron and the positive nucleus. In our assumptions here that one photon is absorbed by one electron, the electrons are found at the surface of the metal and there's no energy dissipated in this transfer. So we can write this out mathematically and say E equals HF equals work function plus a half mv squared. Now remember, the work function is considered a minimum as we assume the electron is at the surface of the metal, so therefore if the work function is a minimum value, that tells us that the kinetic energy of the electron in this equation must be a maximum value. This happens because our photon energy splits between the work function and the kinetic energy. Now in reality you gain a variation of energies, a variety, as the electrons are different distances from the surface of the metal and the actual nuclei themselves. Now, a consequence of the photoelectric effect is that electrons are emitted from the surface of a metal. Now, the true name for the emitted electrons are photoelectrons, electrons produced by photons of light. Now, we can measure their kinetic energy by looking at another property of electrons, which is not their mass or their velocity. What we can do is look at the idea that the electrons are moving in a current off the surface of the metal. Now, the kinetic energy of the electrons emitted is manifested as an electrical current. Now, if we place a negative charge at the opposite end of the metal surface from where they are emitted from, the electrons emitted will be repelled by the negative charge. So what happens is the electrons will slow down and eventually stop moving. So our reading for current will go to zero as the charge is no longer flowing. So the kinetic energy store of the emitted electrons is transferred into an electrical potential energy store. Work is being done. Now, if we again assume that no energy is dissipated in the process, we can equate the two energy stores, and kinetic energy is a half mv squared, electrical potential energy is QV or EV when we're considering electrons. So therefore we can equate the two and say a half mv squared equals EV. So therefore we can rearrange this and say that V in this instance in Vs is the potential difference needed to stop the electrons from moving, the stopping potential. So the kinetic energy is equal to EV, where E is the charge, is 1.6 times 10 to the minus 19 coulombs. Now this assumes the kinetic energy of the photoelectrons is a maximum value, so this is the stopping potential that will stop all electrons. So now we can say our original equation was E equals HF equals work function plus a half mv squared. So now we can sub out that kinetic energy term of a half mv squared and sub in our stopping potential term as they equal each other. Now if we wanted to as well, we could also state that the work function is H times by F0, where F0 is the threshold frequency. Now when analysing the photoelectric effect, we can do this with an experiment and graph various quantities. So what we want to do is measure the kinetic energy of the electrons via the stopping potential concept and alter our photon frequency. So you can do this with the following equipment. We can alter the photon frequency shining lights of different colour onto the surface of a metal. Now the intensity of the light would not affect the results achieved. We can measure the kinetic energy of the electrons with the monitor of the stopping potential on the voltmeter. The stopping potential will be the value of the potential difference which causes the electrons to stop flowing, and this will cause the current in the circuit to be zero. So to find the stopping potential, you alter the PD and record the value of PD, which causes the current on the ammeter to read zero. Now again, we can use the stopping potential to then calculate the kinetic energy of the photoelectrons. Now you can then plot the idea of the kinetic energy of the photoelectrons against frequency. Now the greater the photon frequency, the greater the energy inputted into the surface, the greater the emitted kinetic energy of the electrons. So you can see the following graph. Now the graph does not intersect at the origin because of the work function of the metal. We can extrapolate the line back to actually determine our work function of our metal. So if we have kinetic energy as our y-axis, we have frequency on our x-axis. This tells us that the negative of the y-intercept is the work function. It tells us that the x-intercept is the threshold frequency, and it tells us that the gradient of our line produced is Planck's constant. Now this means all metals will produce lines of best fit of the same gradient as each other. So it's important you can use kinetic energy frequency graphs to work out the following properties. The gradient is Planck's constant, the y-intercept is the negative work function, and the x-intercept is the threshold frequency. And we can use this to determine different properties about the photoelectric effect. Now the next topic we're going to look at is energy levels and photon emission. Now Bohr suggested that electrons do not orbit, rather they exist in energy levels or shells or orbitals, which can be imagined a bit like a flight of stairs. We have the nucleus at the bottom and outer the atom at the top. Now each step is an energy level that the electron can exist upon. So we can call that an orbital, energy level or shell. Now the energy levels close to the nucleus have a low energy because there's a high electrostatic attraction binding the electron and the nucleus together. The energy levels far away from the nucleus have a high energy as they have a low electrostatic attraction binding the electron and the nucleus together. We call the energy level nearest the nucleus the ground state. We call the outermost energy level from the nucleus the valence state. Now an electron can exist on an energy level without losing any energy. It has the the energy of that level, but electrons cannot ever exist between the energy levels. So whilst the original nuclear model had this idea, in fact we believe that electrons exist in stable energy levels around the nucleus. Now remember our rules of our atom. The electrons can exist on different energy levels but not in between. The ground state is the state closest to the nucleus. The valence state is the outermost state from the nucleus. Electrons can transport to higher levels, but that requires energy, and electrons can transport to lower levels, but that requires energy being transmitted to the surroundings. So in this example, the atom has three possible orbitals, so there are three possible energies the electron can have to exist within this atom. So it is here, or here, or here. Now the shell at the bottom represents the innermost shell, or the ground state. The shell at the top represents the outermost shell, or the valence state. So if you had an energy level value for your energy level, it will tell you the energy you need to exist at a particular energy level. Now the lower the level, the less energy is needed, because it's easier for the electrons to exist near the nucleus, because there's a greater attraction from that nucleus. Now if you want an electron to move up an energy level, it needs to be given the exact right amount of energy to move to the correct level. So if more or less energy is given, it does not happen. Now this is true if it's a photon exciting an electron. A colliding electron with the atom can provide this energy to cause this to move up, but it can keep its remaining energy after that. Now when an electron is moved up an energy shell by being given energy, we say it is being excited. We've had the process of excitation. So for example, if you have a photon being absorbed with a difference that is not the energy level difference, then nothing would happen. So 23, 27, 32 would not happen. But if you had a photon with enough energy to cause an exact difference, like such as 30 joules, that can cause an electron to move from level 2 to level 3, because that's an exact energy level difference between the levels in the atom. So in this case, it will cause it to jump up. Now to work out if excitation occurs, you work out the energy level difference and see if the photon has that exact energy. This is the reason why the electron needs the exact energy, because it has a wave nature. The electron is switching frequencies, similar to how a standing wave is formed of discrete frequencies on a string. Now the fact that either the photon supplies the energy or does not supply the energy for excitation is further proof of the particulate nature of radiation. So it is proof of the particle nature of light, because one photon can only absorb one electron at a time, similar to the photoelectric effect. Now it's important to note that the electron does not travel between the shells when it jumps, rather it disappears from one shell and reappears on another. There is a quantum leap that takes place. Now it's important to note that if the electron receives more energy than the energy needed to leave the outer shell, the top level, the electron will leave the atom. This is called ionization, and the energy is given by an electron colliding with this atom. Now it could also be any other particle, but it's most likely going to be another electron. Now it's a common misconception to think that the electron is ionized when it reaches the outer shell. No, it needs to leave the outer shell and reach the ionization level. Now unlike excitation, ionization can occur when the energy level difference or higher is given by a photon, and the excess energy goes to the kinetic energy of the electron emitted. Now in ionization, not all of the kinetic energy of a colliding electron needs to be passed on to the atom in a collision. It is very similar to the photoelectric effect. Now the photoelectric effect is similar because it's the ionization of electrons from a metal surface due to the absorption of electromagnetic radiation. Now ionization in general is just the emission of any electron from any atom due to energy being given to it. Now it's important to note that you can consider ionization to be like an extreme form of excitation. Now in reality, whilst we might use joules in some examples, it's a lot easier to express your energy level calculations in a different unit, the electron volt, which is the work done when an electron is accelerated through a potential difference of 1 volt. Now 1 eV is 1.6 times 10 to the minus 19 joules. So if you wanted to convert from eV into joules, you multiply your value in eV by 1.6 times 10 to the minus 19. If you want to convert a value from joules into eV, you divide your value by 1.6 times 10 to the minus 19. Now we've talked about de-excitation, but the process of excitation is moving an electron up the energy levels but not leaving the atom, and this can happen when the energies correlate to the exact differences in energy levels. So in this case, the energy required to excite the electron in level 2 to 3 is 1.9 eV. So again, to work out if excitation occurs, you work out the energy level differences and see if the photon has this energy. Now we can represent excitation energies with the following diagram, and these are the energies of the photons that would cause the electrons to move up an energy level. Like we said before, ground state is the lowest possible state of an atom, and the top level is the amount of energy to ionize the atom, which is written with the dashed line as it represents the boundary of the atom. Now the number on the side represents the amount of energy found in the shell. Now the most common way of writing the structure of the atom though is not with excitation energies, rather with ionization energies. Now what this tells us is, once again, the top level is the energy needed to ionize the atom. The bottom level is the ground state, the most stable state of the atom. Now the number on the side now represents the energy needed to ionize an electron found in this shell. So energy levels or ionization energies are always written as negative values because they're relative to the ionization level. So for example, minus 2 eV means that 2 eV is needed for the electron to be ionized. Now we define zero energy as the energy required for the electron to leave the electrostatic attraction of the nucleus. This is because now there's no electrical potential energy between the electron and the nucleus. Now it's important to note that when we're looking at electrical and gravitational fields, energy is always defined as zero at infinity. So we state an object in this case is at infinity if it's outside of the atom. Now, we've got to always give our energy levels in terms of negatives, as the electrons are bound to the nucleus, so require energy to release them. The electrons are in essence in debt to the nucleus, so work needs to be done to an atom to liberate the electrons. So the negative energy means the atoms need to take energy in, work is done from the surroundings to liberate any electrons. So for example, to liberate any electron in an energy level, you might have to give an electron at least 5 eV from energy level 3. Now it's important to note that an electron is excited when it can leave a shell and move to a higher shell, such as this example, but if it does so, it then leaves a space or vacancy at the shell it departs. So atoms don't like to have vacancies in their inner shells. It disrupts their stability, and in addition, the electrons in the higher levels are less stable than the inner shell electrons, as they need more energy to exist in these levels. So sooner or later, the vacancy is filled by an electron from an outer shell dropping down, as the electrons prefer to exist at lower energy levels as they are more stable. Now which one does this is dependent on probability. Now this is why electrons fill up with certain shells first. It's more energetically favourable to do so. So when an electron goes down levels, the excess energy of the electron is shed as it moves down, which we call de-excitation or relaxation. Now in de-excitation, the excess energy shed will be as a photon. Now this photon will have an energy equal to the energy level differences of the levels. Now atoms can only release photons of certain energy corresponding to those energy level differences. Now in this case, it will be going from minus 2 to minus 15, so the energy of this photon is 13 eV. That's the energy the photon released from the atom. Now this explains why certain substances fluoresce or glow with visible light when they absorb radiation. It's why different elements glow with different colours in the chemistry flame tests. Red visible light is longer wavelength light, so the photon produced from a small energy level difference that the electrons are moving between in the atom. Blue visible light is shorter wavelength light, and it's a photon produced from a large energy level difference that the electrons are moving between in the atom. So if the energy level between the energy level difference in the two levels is small, then the photon produces in the infrared spectrum. If the energy level difference between the two energy levels the electron moves between is very, very large, the photon produces in the ultraviolet spectrum. Now this explains why ultraviolet photons are so rare. You need a large energy level difference in your atom to produce them. So excitation is the process of electrons moving to higher energy levels from lower ones. It's an instantaneous process, and it requires energy to be placed into the atom. Now excitation can occur either due to the absorption of a photon by the atom or by the transfer of kinetic energy from a colliding particle such as a free electron. Now excitation requires the exact energy level difference between the levels to take place in in the atom. Now the photon will require the exact difference between the two levels, otherwise excitation will not take place. A colliding particle such as an electron will only lose the exact energy level difference from its kinetic energy store. Now de-excitation is the process of electrons moving into lower energy levels from higher ones. De-excitation is an instantaneous process. De-excitation releases energy from the atom in the form of a photon. The energy of the photon released is equal to the energy level difference between the two levels the electron moves between. The larger the difference in values, the greater the energy the photon has. The smaller the difference in values between the levels, the lower the energy the photon has. So we can look at this and explain why certain substances fluoresce. Atoms in the substance will absorb energy and become excited. When they de-excite, they emit visible photons. This means when the original source of excitation is removed, the substance will stop glowing. An example of this is going to be a tube such as this, a fluorescent bulb, because what happens is you have an electrical current through your tubing that will cause excitation to the atoms inside the tubing. They will then relax or de-excite and they will release photons, which you can observe as visible light. So what we're going to look at is this idea of fluorescent lamps now, of electrical current, excitation, relaxation, photon emission. So a fluorescent tube works as the free electrons flowing through the tube due to the current hit the mercury atoms inside the fluorescent tube and excite them. Now this is caused by applying a high voltage across the fluorescent tube. Some of the atoms will also be ionized by the collisions with the free electrons and each other. Now eventually, after excitation has occurred, the mercury atoms de-excite and emit photons of energy as ultraviolet radiation. This happens as the energy level difference between the different levels in mercury equates to UV photons. So what then happens is the photons of UV radiation hit the phosphorus atoms on the surface of the tube and excite them. This happens as certain energy level differences in phosphorus allow for UV photons to be absorbed to cause excitation. Eventually the phosphorus atoms de-excite and release the energy as visible light photons. This happens as certain energy level differences in phosphorus equate to a visible photon. Now there are certain energy level differences in phosphorus that equate to UV photons being emitted, which is why a lamp is never 100% efficient. So stage 1, ionization and excitation of the mercury atoms occur as they collide with each other and electrons flowing through the tube. Over time the mercury atoms emit photons when they de-excite in both the UV and visible spectrum. The UV photons are absorbed by atoms of phosphorus coating on the surface of the light, which excites these atoms. They then de-excite and emit visible photons. Now it's interesting to note that when we shine light through a prism we get a continuous spectrum because there's no break in that spectrum. However, if we place a cold gas between the light source and the prism, some of the lines of the spectra disappear, so we call that an absorption line spectra because the cold gas was absorbing some of the energy from the visible light source. Now sometimes if we look at the spectra given off by a hot gas placed through a prism, we can see lines of the spectrum appearing, which we call the emission line spectra. Now this occurs as the hot gas is only emitting certain frequencies of energy. So we can have our continuous spectra, our emission spectra and our absorption spectra, which tend to be opposites of each other. So let's try and understand the physics behind this. Line spectra provide evidence for the transition between the discrete energy levels in atoms. So let's consider how they work. So what happens is when de-excitation occurs, the electrons drop their levels, they will release a photon of a certain energy which is equal to the energy level differences, and that can then form a line on your emission spectra. Now the number of possible jumps downwards gives you the number of possible lines in the spectrum. So it's an important idea to note that the number of lines in the spectrum tells you the possible jumps in the energy levels of an atom. Now the emission spectra is unique for elements as each elements have a different energy level number, so a different energy level difference, so it means they will emit photons at different frequencies, and the frequency of the photon absorbed in the absorption spectra is the same principle, just the other way round. So again, you need to be having the exact energy level difference between two levels for your photon to cause excitation of electrons, and so you can work out what the energy of the photons need to be. So this results in a dark line in your absorption spectra, because if the energy of the photon is the exact difference of two levels, that will be taken in by the atom and cause excitation excitation. So our black lines are the actual values of energy, which are exact energy level differences and cause absorption to occur in your atom. So again, it's unique for every element, as each element has different energy level differences. So an emission spectra is caused by de-excitation, by the atom emitting photons, and the absorption spectra is caused by excitation, the atom absorbing photons. But they're both caused by electrons moving between energy levels. The emission one by electrons moving down the spectra, and absorption by the electrons moving up the particular levels. So spectra only occur as the atoms carry out excitation and de-excitation. So they are experimental proof of the particle nature of light, in addition to the photoelectric effect and the ultraviolet catastrophe. Now, as the line spectra of each element is unique due to each element having different energy levels, you can identify elements present in a sample, because you'll excite a sample of a substance, let the sample de-excite and record its emission spectra, compare the emission spectra with known samples and find the matching element from the matching sample. Because it doesn't matter where the sample is excited, the line spectra will always be the same. That's how we determine what was inside objects like stars, like the sun. We can determine what is in supernovae, and we can determine if an object is redshifting or it's not by looking at their line spectra. So emission spectra show the wavelengths of different photons emitted by atoms when they de-excite. The absorption spectra show the wavelengths of different photons absorbed by atoms to excite the electrons. So if we look at this example, an electron in the fourth shell could de-excite to the third, to the second, or the first shell. So what happens is when they do this, they release a photon with an energy equivalent to the difference between the two levels they're moving between. You can then use this to work out the wavelength of that particular photon. Now, it's important to note the energy when you do this must be in joules, not eV. So you can do this for every single transition in an atom. So you can find them from 4 to 3, 4 to 2, 4 to 1, so on, so on, so on, and work out the wavelength of each one, and then link this into the emission line spectra, because you have your lines of your spectra which are equivalent to those transitions. So the photons in the same spectral line have the same fixed amount of energy unique to that line. The higher the energy photons are found to the right line side of the spectra, and then the low energy photons are found to the left of the line spectra. So it's important to note that if E equals hc over lambda, the greater the energy level difference, the shorter the wavelength. So the largest energy level difference in your atom produces the shortest wavelength. The smaller the energy level difference, the longer the wavelength of the photon emitted or absorbed. So the smallest energy level difference produces the photons of the longest wavelength. So each coloured line in a line emission spectrum corresponds to the wavelength emitted by the source. The photons that produce each line have the same energy unique to the spectral line. Each photon is emitted when an atom de-excites, and an atom only emits particular wavelengths of radiation because the electrons in it can only emit photons with energy equal to the difference between two of its levels. Now, no two elements can produce the same pattern of wavelengths because the arrangement of energy levels in atoms are unique to each element. Now, it's important to note that an absorption spectrum has black lines that arise from only particular wavelengths of light being absorbed by the source, because the electrons can absorb photons with energies equal to the difference between the two levels. So let's now consider the collision of electrons with atoms. So excitation occurs when the electrons move up the energy levels, which can either be given when it receives energy from a photon or receives energy from a collision with another electron. Now, excitation is instantaneous and proof of the particle nature of light. So what can happen is in excitation, the electrons move up energy levels. Now, an ionization is similar to excitation, however, the electron is considered to be free. So in your collision for your ionization, the electron will in fact leave our atom. So you can compare and contrast the two. Now remember, adding electrons makes an atom a negative ion, removing electrons makes an atom a positive ion. So it's important to understand the difference between ionization and excitation. Ionization is caused by the collision of a particle with an atom, normally an electron, okay, and then this gives the electron, or in the nucleus, energy. So the electron colliding with an orbital electron can also cause excitation. Now, the kinetic energy of that first colliding electron is passed on to the second electron inside of the atom, and this causes the second electron inside of the atom to either be excited or ionized. Now, this means that the first electron can actually stop moving. So both ionization and excitation are caused by an atom gaining energy via a collision with the fast moving electron. Now the fast moving electron is moving in an electrical current. Now this causes kinetic energy to be transferred from that fast moving electron to the actual atom. Now the electron can transfer all of its kinetic energy and stop moving, or it could in fact just slow down. Now the free electron only has to transfer enough kinetic energy in the atom to excite it. This means it could continue to move after its collision. Now the energy transfer to the atom can also cause this excitation process. So what then happens is the atom will eventually relax and release a photon of energy corresponding to the energy level differences of the two levels. However, the electron here has stopped moving or has at least slowed down, so the current dips if excitation occurs. Now if the colliding electron does not have enough kinetic energy to cause excitation, it is deflected by the atom with no overall loss of kinetic energy, and an electron absorbs exactly the right amount of energy to move between the two levels after colliding with that free electron. And that contains the same energy or greater energy than that is required to change the levels. Now as energy is conserved, the energy gained by the electron inside the atom is the energy lost by the electron colliding with the atom. So the free electron's kinetic energy after the collision is the same as it was before, minus the energy transferred, which is equal to the energy level difference inside of the atom. Now we can also have ionization in collision. Now this occurs if the fast moving electron transfers enough energy so it moves above the ionization energy of the atom. So in this process the atom will release an electron due to the ionizing process. So whilst the original electron can stop moving or slow down, another fast moving electron has been released from the atom to replace it. So therefore the current will stay the same value. Now in addition, in ionization, the original colliding electron does not have to transfer all of its energy to the atom, so it could be still moving as well. The conservation of energy still applies in this situation. So the idea is any energy above excitation or ionization remains as kinetic energy of the electrons or of the recoiling atom. Now when an electron collision causes an atom to be ionized, there's no observed dip in the current. Now in wave-particle duality, we say electromagnetic radiation has a dual nature. It can behave as a wave or a particle. Diffraction and interference, it must be like a wave. Photoelectric effect, it must be like the particle model. So in 1924, Louis de Broglie hypothesized that particles of matter like electrons should have wave properties. In his PhD thesis, he said if wave-like light shows particle properties, then particles like electrons must show wave-like properties. Now most physicists at the time were not accepting of this theory, but over time his work was evaluated by peer review and his hypothesis was then confirmed by experiments. So this theory has now been accepted to be true unless any new conflicting evidence comes along. So de Broglie's work is an example of how the knowledge and understanding of our nature of matter has changed over time. So all matter can display wave behavior, so has a wavelength called the de Broglie wavelength, which is equal to h over p, the Planck's constant over the momentum. Now momentum is also written as mv, so you can write it as wavelength is equal to h over mv. That's very, very important. Now this equation can only be used for matter particles, so therefore it can't be used to work out the wavelength of a wave. Now the wavelength of the wave wave nature of the particle can determine its properties. The more massive a particle, the smaller its wavelength, which is why we don't observe wave behavior on massive objects such as humans. The faster we move a particle, the smaller its de Broglie wavelength becomes. If a particle is stationary, it exhibits no wave properties. It has a wavelength of 0. If a particle is stationary, it is purely matter. Now the mass we use in this equation is the overall mass of the particle, the rest mass plus the relativistic mass. Now all matter has a de Broglie wavelength, which we can use to determine their wave nature. Now one famous mechanism, which is a wave property only, is diffraction. So it means that if a wave passes through a gap similar in size to its wavelength, it will diffract. Now in a similar idea, if matter passes through a gap with a gap size similar to the de Broglie wavelength, the matter should then diffract. So you can get an electron diffraction pattern forming on a screen, because in this instance the electrons have moved through a gap of similar size to the de Broglie wavelength of the particle. So you can get an electron diffraction pattern forming on a screen. So when electrons pass through graphite, they will pass through gaps in graphite similar to their de Broglie wavelength. They'll hit a luminescent screen and produce patterns of rings associated with diffraction. So this was proof that electrons and all particles have a wave-particle duality. The production of rings indicates an interference pattern. Constructive interference takes place where the bright rings form. Destructive interference takes place where the dark rings form. So it's conclusive proof that electrons must be exhibiting wave behavior. If the electrons were exhibiting particle behavior, you would only see a dot. Now, when you carry out this procedure, your velocity of electrons have to be carefully monitored because it can alter the size of your de Broglie wavelength. Now, the diffraction pattern is not observed with humans walking through gaps, as our de Broglie wavelength is much smaller than the gaps we travel through, which is why we don't observe our wave behavior. But all matter does have a wave nature, and if electrons pass through a gap, such as graphite atoms, the de Broglie wavelength of the electron is similar to the gap size between the graphite atoms, so you will observe this diffraction taking place. So this interference pattern is proof that the electrons have diffracted through that gap size. Now, from the nuclear atomic model, we can then understand why the atom is mostly empty space, because the atom is mostly empty space to fit the wavelengths of the standing electron waves in there. So the atom is mainly empty space because the electrons exist in waves around the nucleus, not as particles, and we need this space to fit in our wave. So the radius of an atom equates to the largest wavelength of the electron in the atom, which can be visualized as the longest wavelengths, as these are the electrons in the highest orbitals. So actually, a nucleus is not a an atom is not a nucleus which has energy levels around it. It is in fact a nucleus with a series of electron probability waves existing around it. The electrons form different standing harmonic waves around the nucleus. So let's summarize what we've learned. We should understand threshold frequency, the photon explanation of the threshold frequency, work function, stopping potential, and the photoelectric equation. We should understand ionization, excitation, and understand the idea of ionization, excitation in the fluorescent tube, understand the electron volt, understand line spectra as evidence for the transition between discrete energy levels in atoms, for linking in here with HF equals E1 minus E2, and have an understanding that the electron diffraction suggests that particles possess wave properties, and the photoelectric effect suggests the electromagnetic waves have a particulate nature. You should be able to understand the de Broglie wavelength, which is lambda equals h over mv, where mv is momentum, be able to explain how and why the amount of diffraction changes when the momentum of the particle is changed, have an understanding of how the nature of matter has changed over time, and have an appreciation that such changes need to be evaluated through peer review and validated by the scientific community. So I hope you've enjoyed this revision session on quantum physics. Thank you very much for listening, and have a lovely day.